To get started with our seminar today, it's my great pleasure to introduce Professor Mohammed Ashraf Alam from Purdue University. Actually, I happen to know him very well. At least, what, 20 years?
20 years.
And I used to know him first as a student at Purdue University. We had a lot of interaction at the time with this group. After graduation with his PhD, he joined Bell Lab Laboratories. Was a member of technical staff in the Silicon ULSI Research Department from 1995 to 2001. Then was, from 2001 to 2003, a distinguished member of technical staff at the Gear System. And then he returned to Purdue as a professor in 2004. And he is an expert in physics, simulation, characterization, and technology of classical and novel semiconductor devices. He's very involved now with like nanosensors and the like. Has widely published over 200 papers in international journals, and has many, many invited presentations, and is a recipient of honors like the IEEE Fellow, American Physical Society Fellow, and Fellow of the American Association for Advancement of Science. And also he was a recipient of the 2006 IEEE Kiyo Tomiyasu Award for contribution to device technology for communication systems. So I'm very pleased to have you back to visit us, and I can't wait to hear your talk.
Thank you very much. So first of all, it's always a pleasure. I came here when Beckman Institute was just being opened, probably at that time. And so it has a lot of pleasant memories. We often used to drive here with my advisor and then listen to various talks. And I think you just joined at that time. So let me tell a little bit about my talk today is about limits of nanobiosensing. That's the first part. And then how to break these limits. And when we started working on these problems, this notion that there are fundamental limits to biosensing was not so clear. People would publish different results with extraordinary sensitivity of the sensors, and this would appear in very prestigious journals. And there is no way to know that if there is any basic limit that you should check your results against. So first part is about the limits, and the second part is how do you overcome the limits. In both cases, nature will tell us or guide us towards that goal. So just a brief background of today's talk. But we have a center called Nanohub. This is sort of a hosting center like Amazon.com, and which essentially takes content from a wide variety of places and hosts it. And many of you may have used it for various simulation or courses. Has more than 300,000 users who use it routinely. Now, the content generators for that quote-unquote Amazon are this type of different organizations. One would be in the NEEDS node that's hosted at, led by Purdue, and Stanford, Berkeley, and MIT are part of it, and Nanobio node that is sort of led by Illinois. And these different organizations create content for the Nanohub. And recently I taught a course on nanobiosensors, and so that it is a part of the Nanohub University curriculum. And I hope that you will take in, because everything that we will say in summary is essentially discussed in a more detail in about 30 lectures or so. And it has a series of, it goes with a software that has all the homeworks associated with this course. And my hope is that we'll be able to collaborate with this Nanobio node so that these things can be cross-linked and we can learn from each other. So the reason biosensors are very important is because there have been a convergence of sorts going on. And for computing, there have been tremendous advantages. 50 years ago, there would be all this magnetic tape. You may not have seen any of these. Unfortunately, I'm old enough that I have seen many of those. And today, of course, all those are in an integrated circuit that has more processing capability. than most of the older computers would have had. Communication, very similar. One-way communication of radio, and then you have this cell phones. And if you are a fan of older movies, then you know some of the older movies have some of these big-sized cell phone, even James Bond movies, that doesn't look very sophisticated. And of course, computing and communication have come together very beautifully on this iPhone-type platform. But what is really missing in the system is the healthcare. Healthcare is yet to come in a fundamental way. Any barber shops, you will see that bandage, this circular red thing, is actually a symbol of the bandage, because they used to be, the barber used to be the chief surgeon of a town. And so therefore, things were not very pretty in that place. So that's where the symbol comes from. These days, you package it in very sophisticated package, but still things are pretty big. And someday, if you want to really pull everything together, what you need is sensors which are much small compared to what we have now. Then there are millions of them, well integrated with silicon technology in some way. And that will be eventually the goal. And if we are lucky, then you may someday look like that. But the idea is that this synthesis is one of the fundamental drivers of modern technology. And almost all companies that I know of, I work with a lot of companies, each one of them, TSMC, Samsung, and Qualcomm, all these companies, all working on sensors. So that, because they know that if they want you to pay more, you are not going to pay too much more for iPhone. But if you had a sensor that could sense glucose or blood pressure in a continuous way, you are willing to pay a little bit more. So there is a lot of economic and technological incentive of why sensors are important. So this is my recent blood test. I hope there's no doctors in the audience, so nobody will tell me that I am in a very bad shape. But the idea is that if you look at your recent blood test, you will see that the concentrations are very high, most of the concentrations. And these are in the millimolar level. Molar concentration is generally a water. If you just take normal water, that will be 55 molar or so. And most of the time, 100 millimolar would be your salt concentration of the body. And generally, you see that the sodium, potassium, all those things are in millimolar concentration. Now, these concentrations are so high that when you take a Tylenol, within minutes, it begins to work because the concentration goes up by in the millimolar range. So therefore, it sort of floods your entire body with high concentration, and that's why it works so quickly. But what you really want is that not to look at things in the millimolar level. Of course, by the time something shows up in the millimolar level, these macro indicators, things are in some way already in a bad shape. You know, most of the sensors, it is not surprising that most of the sensors are associated with an organ, meaning that lung cancer or this cancer, that cancer, because we cannot really detect them early enough. By the time we detect them, some organ has been damaged. If we could somehow detect them much earlier, then that would have been a fantastic ability. Of course, we have to avoid false positive. That's a big concern in the sensor field. But if we could detect things at a lower concentration, perhaps we could have some intervention a little bit earlier. So the question that I'll be asking in today's lecture or this seminar is that how do you go from high concentration sensors to low concentration sensors? What are the fundamental limits? And if there is some fundamental limit, can you break it? And it turns out, as I said in the beginning, that nature knows those limits, works by the limit, and from time to time, as necessary, breaks the limit all the time. So we'll see how that works. And the goal is that if you really knew the low concentrations, then like a Google map, you'd be able to know all the pathways and the interconnections. Right now, if you have a headache, it's like carpet bombing. You just go there, flood it with medicine. All the local networks may be disrupted. You don't care. Yeah, so in order to solve one problem, you have many other problems you create. If you knew all the pathways, then you probably would be able to design drugs that would be somewhat more specific. So when we started working on this about I'd say 8-9 years ago, the first thing I come from electrical engineering background, semiconductor device physics. That's why I used to come here often to the Beckman Institute. Professor Carl Hess, Professor Ravioli, all those people used to do fantastic work. They still do, I'm saying. But so I come from a device physics background. I'm simply asking the question, well, you have so many sensors. And some sensors, they can detect picomolar, some nanomolar, some attomolar, and everybody has a different number. Now, a paper is published. How do you know whether this number is reasonable or not? Because a student could make a mistake, or there could be a typo. And at the end, only thing before when I came to the field was that you had to trust that advisor or that group. They couldn't try, there was no number or no way to know whether something is reasonable or not. So I would try to provide a quote-unquote Mendeleev table for these sensors to know, given a structure, what is possible. So what was the traditional explanation of high sensitivity? Everybody knew that if you go to nanoscale, if you go to nanoscale, things would be much better. Everybody knew that. And the explanation that paper after paper would come, it would say, because now you have increased surface to volume ratio. Surface to volume ratio, therefore the sensors are more sensitive. Well, you can easily go in and calculate, because this is like a transistor, and we know how a transistor works. So you can go and look at the typical diameter of the nanowire sensors. So you can see that electron is flowing from the source to drain. These are the receptors. And when these target molecules come in, they change the charge, and therefore the current changes. And so therefore, you are trying to, given the diameter, you could calculate what would be the change in the conductivity, conductance relative to this original value. And it turns out that, yeah, you do get, as radius gets smaller, you do get a factor of 3, 4, 5. But we are talking about 6 orders of magnitude enhancement in sensitivity. There is no way surface to volume ratio would explain anything in this type of sensors, because it is simply, this is something that sounds reasonable, but it is simply doesn't hold up to back of the envelope calculation even. So therefore, at that time, the insight that I had was that these biosensors are not very different from a jellyfish, because just like a jellyfish catches its geometry, uses its geometry to sit still and still capture the biomolecules from the surrounding, a sensor, a nanowire sensor, and a jellyfish fundamentally cannot be different. It is trying to optimize two things. It is trying to increase the surface area so that it can capture more. But then it has to, of course, pay a price, because it has to do transport of those molecules to wherever the other places it needs to be. So it's trying to do a balance. So that if I understand this jellyfish, I'll understand a sensor. That's the strategy. Now, let's see to what extent, this looks too complicated, to what extent we can succeed. It turns out it will be very, very simple, actually. So I'll talk about 3 things then. One is this settling time. The second one is sensitivity. And third one is selectivity. You should always, anytime if you are working on sensors, these are the 3 things you should always be thinking about. I want to first distinguish between settling time and sensitivity. Settling time is how long does it take before a biomolecule comes to your sensor. Think about it. Let's say you are looking for a rare bird in Amazon. You have a megapixel camera, very sensitive, very sensitive. But first of all, you have to see the bird before you take the picture. It doesn't matter how sensitive your sensor is if the bird doesn't exist. Then therefore, sensitivity doesn't matter, or if it's very rare, then you need, so the sensitivity is your megapixels in your camera. Settling time is how long will it be before the bar comes in your view. And selectivity is you are taking one picture, but you want to take the picture of the bird. Of course, if there are 10 other birds in the same frame and you cannot distinguish them, then that picture is not very useful. So these are the three things that we'll think about. And these are all fundamental in the sense that there's nothing about silicon-based transistor or nanoparticle or plasmonics or any other things. Those would all come under sensitivity. But settling time is technology agnostic, that it doesn't matter which technology you are looking into, all technology will behave the same way. So let's start with a simple planar sensor. The sensors, those would be older technologies, which are not as sensitive, can detect millimolars, remember my blood test, those type of thing. What is the idea? Well, you can do a very simple calculation. Assume that this is a sensor. This could be a transistor, or you could tag with some fluorescent molecule, whatever, and the molecules are coming from the and assume that it's flat. Now, this is the molecule side view, and this is the sensor. So you can make a very simple calculation. You can simply say that if you allow a certain time t, then the molecules will randomly walk around, and like a blotting paper, they will be absorbed on the sensor surface. And let's give it as benefit of doubt that everything that gets attached never gets detached. So it is perfect capture. So that will be the best that you can possibly get. And so the amount that got depleted within time t is square root of dt. That's the diffusion distance. And you can easily calculate how many molecules do you capture within a given time. N of t is the number of molecules that you captured. A is the area of that sensor. Rho is the density. If it's a high density, then you will capture more. If it's a low density, of course, in a given time, you'll capture less. It's like putting a thermometer in a child's mouth, because if you have high fever, in a very short time, the thermometer shoots up. Fever is low, then you have to wait longer before you can detect how much fever there is. And this rho naught is the density. R is the distance through which you captured things. This is square root of dt. So if your sensor requires a certain number of molecules before it you can detect it, let's call that number n naught. And so you immediately realize that there is a limit, settling time limit, that goes with the square of this density. So if you have 1 molar, then let's say you have a certain time constant. Then if you have a millimolar, the time immediately will go up by a millionfold. This is the simple statement of this two-line equation. Dramatic consequences. Yes, by making a sensor much more sensitive, you can reduce NS from 100 to 1. You can do that. You can, by making the molecule smaller, you can increase the diffusion coefficient. That you can do. But this is a very simple relationship that tells a millionfold increase when your concentration has gone down only by a factor 3 orders of magnitude. That's really not very good. Now, it immediately connects here with something called a fractal dimension. This 2 is really the dimensionality of a surface. Now, I'm not going to explain all the details of a fractal dimension, but you may remember from when you were in high school or in college that a surface is a two-dimensional quantity, right? Geometrical quantity. A line is one-dimensional. A dot is a zero-dimensional quantity. And so, therefore, it will turn out, I'll show in a second, this 2 depends on the dimensionality of the surface. How do I know? Let's look at another example. Assume I have a nanowire. If I have a nanowire, and if I take a cross-section around this, then my analyte is on all sides. I know, then the bottom side, this is not a perfect picture because I should have drawn half the circle. I realize because this is a plate in here, but just to make a general argument that if you have a nanowire hanging in a solution like a thermometer inside, the question is how many molecules is it going to capture within a certain time t. Now, to the 0th order, you may think that result will not be very different. Turns out it is going to be very different. The reason is that when it captures, still this distance, the capture radius is still square root of dt. However, the number of molecule captured multiplied by the surface area, which is 2 pi a, will be rho naught pi r square, because that's the region from which the molecule was captured. This pi r square is very important because you see what it does, that generally what happens in a one-dimensional system, that there is a square root of dt. Longer the time, fewer the molecules which are captured. So this is called a diffusion slowdown. However, if you sort of capture from a larger and larger area, it can cancel the diffusion slowdown. So effectively, although it's a diffusive system, there is no diffusion slowdown in such a structure. And so therefore, again, you put that you want to capture a certain number of molecules before it gets activated, and then you rearrange the term a little bit, and it says that Ts of this structure is going to be inversely proportional to rho. No, not rho squared. So that means if you go from 1 molar to a millimolar, now the time will increase by 1,000-fold, not million-fold. And so therefore, this is a dramatic enhancement in the time to capture this. So for a given sensitivity, a given density, you'll be able to also detect it in a shorter amount of time. Right? So this by the way, all these things are, of course, simulated in much more greater detail. After a PhD of a student is done, of course, by that time, we understand things much more simply. I'm telling you the simpler version. The real pain and suffering of the graduate student are all hidden in the approximation sign. Now, if you give me that this dimensionality, this rho to the power 1, is related to the response time, then I can do something which is really dramatic, which is a sensor which is not, this is not 1 nanoware, but a bunch of nanowires. Now, you may think that if 1 nanoware is good, 10 nanowares is better, right, in terms of sensitivity. In fact, 2 companies were founded on this premise, that if 1 nanoware is good, 10 is better, 100 could be even better. But what I just told you, that should not be, you should not be so sure anymore. Because after all, when the biomolecules come, all these sensors they will sort of compete against each other to capture the same molecule. And they have the increased width, so therefore the sensitivity may not be as high. In fact, it could be in between. So let me so this part I'll go quickly, but just to give you an idea, there is no simulator that can actually handle a diffusion problem like this. Maybe, I don't know, maybe in Illinois you may try it, but generally it's such a complex system. This is something that we used to work with Professor John Rogers on carbon nanotube network, and correspondingly it's such a complex system. You can do the transport, but a 3-dimensional diffusion to a network like this would be very difficult to solve. Fortunately, you don't have to solve it. It turns out that this surface, the way it captures the particle, it turns out that you can correspondingly make an array of sensors. So these are like 1-dimensional sensors with a certain spacing. And you can show that the physics of capture of this complex surface is exactly the same of the physics of capture of this surface. It is like Fourier transform, right? Sometimes it's the same, it has the same content, physics content, but simplifies the math. So this is called a Cantor transform that takes a complex structure and creates a equivalent structure that allows simpler solution of the diffusion equation.
With the same diameters?
These are same diameters. So Cantor did a 1-dimensional thing, and so these spacings are different, but the diameter is fixed.
So this lower diameter is the same as the upper diameter?
The lower diameter is the same as the upper diameter.
What's the physical basis?
The physical basis is that, let me show you in the next one, because I have a little animation that will make things a little clearer. But this spacing has to be done right. So the basis is something like this. So let's say This is the diffusion field, how it evolves. What happens that when you are very close to the first surface, essentially the diffusion field is two-dimensional. A little bit later, the diffusion field of the neighbor, they begin to merge, and they become one-dimensional. A little bit later, and then this becomes together, it behaves like a single element. So it's scale invariant as you're going up in the diffusion field. And so therefore, the solutions, because they are scale invariant, it cannot decide whether it's a one-dimensional surface or two-dimensional surface. In the beginning, it looks like a one-dimensional surface. So it behaves like this. A little bit later, two-dimensional, one-dimensional, two-dimensional. And this transition, where it goes from 1 to 2D, that depends on the fractal dimension. If you have very low density, it will behave like a 1D all the way. If it is very high density, it will behave like 2D all the way. In a self-similar structure like this, it goes as 1 and 2D, alternates between them. And the transition depends on the density. And so at the end, you can show that the formula that will capture all surfaces is very simple like this. Number of molecule captured is proportional to the density of analyte, time that you are willing to wait. Let's say you want your test results tomorrow, by tomorrow. So in TS, you will put 24 hours. That's the TS, the time that you are willing to wait. 3 minus df over 2, df is the fractal dimension. So a surface is two-dimensional, right? So ds would be 2, so there will be TS square root. If it is one-dimensional, then it will be one-dimensional, so it will be t to the TS to the power 1, and anywhere in between. So this is a general formula that should capture all responses. And so you can plot some results now. I have to plot a log-log. I'm plotting a log-log version. In the x-axis, I have the density, micromolar to a femtomolar, and a millisecond to 10 years. 10 years, yeah, it's about 10 years. And so if it's 1D, a planar surface, 2D, then you realize that this would be a straight line with a slope of -1. Right? So a slope of half. And you can see just from here, 6 orders of magnitude here, and then 12 orders of magnitude in the vertical axis. So you can see slope is half. And if you are willing to wait only 100 seconds before you want your test results, there is no way that you can detect less than a nanomolar. Any paper that says that you can detect further, there is something more going on. There's not possible in the diffusion limit. In that sense, it's fundamental. Nanomolar is what you can detect with a planar sensor. Now, if you, on the other hand, do a composite, it will have somewhere in between. But if you have a nanowire, you can see the nanowire on this axis and on this axis is 1 to 1. Slope is -1. So a nanowire immediately will give you several orders of magnitude improvement because it beats the diffusion slowdown by the geometry. It's capturing from all sides. And the place where it's capturing from gets larger and larger. So this was the first paper in 2006 or 2007 when we predicted that this would be the limit. And we couldn't find too many papers. But essentially, there were few papers that we could find, and more or less everybody had this general rule. Many of these papers, or at least some of them, have subsequently revised upward. In fact, there was one retraction in Nature based on this data. But I want to show you, this was sort of a bold prediction at that time based on a relatively simple analysis. And there is this variability as things become smaller, there is variability in the response. But last year, there was this paper from Ruckus group. They plotted everything that they could find. Look at the scale. This is in 1,000 minutes to 0.04, attomolar to a micromolar, similar, just the axis reversed. All the sensors that they could find follows essentially the same scaling law. So anytime, I'm saying this is 0th order, right? It's not a sophisticated calculation. To 0th order, that it is not possible to go below this line. You can, anytime you do a new sensor, it will have a new types of values. It will be somewhere. But this line is a fundamental diffusion limit line. And it is not possible to do bit diffusion until you are very clever.
So if you add convection to it, then you might enhance.
This is sort of, professor is asking a very important question. So in the beginning, this is something, again, is a very interesting. So what happens that people thought that if I have convection, then things would improve dramatically. It turns out the only time you can have improvement, and this comes from larger structures, intuition from the larger structures, because the stagnant layer, when it is comparable to the diffusion distance, because you have a certain square difference, for large structures that improvement is dramatic. But as you are getting smaller and smaller, the advantage due to the convection becomes dramatically suppressed. The reason is it can come in faster, it's true, but it can also leave faster, the analyte. And so at the end, you don't win. And in fact, if you use the simulator that we have, and Shinzen, who is a student here, he put together all the simulators from over the years, you can exactly calculate for all velocities, all viscosities, that what type of enhancement you'd get. Nano doesn't benefit much from convection, as you might expect. Right? Yeah, life in low Reynolds number, there are lots of surprises there. All right. So what this allowed us to do is to then look at all sensors in a fundamentally simple, very simple way, and you can organize them. You can say what type of sensors would be helpful. It turns out that if you do a nanowire, and then you say, okay, nanowire is good, nanodot is even better. Turns out nanodot and nanowire has essentially the same response. You cannot go faster than t. That is the diffusion time. A sphere catches molecule is in fact in the same way as a line does. This is just a mathematical statement. So therefore, you don't get any advantage by nanodot. Now, at that time, something very interesting started happening because I began to see there are papers. These I could understand. But there are papers which I couldn't understand and which were saying that they can do attomolar detection. What is happening in here that is not happening in here? Because most of the time, going 10 femtomolar would be very difficult. And anything below, you have to sort of think about it. It turns out this was the first one that sort of quote unquote showed us how to beat diffusion, how to beat this limit. And I'll explain how that works. I thought, what is happening? I thought this is working. Oh, I'm sorry. Okay. So there are 3 ways to beat diffusion, and I'll tell you. And you, in fact, know all of them by intuition. If you want to catch a thief or a robber, there's 2 ways of doing it. You can be a policeman and sit in the station and sleep and hope that if the robber is drunken enough, that he will randomly walk around and give himself up. This is the strategy of our sensors. All the sensors work we do, we hope that the biomolecule will come and then give itself up. That's why it takes such a long time, especially if the density is low. So what do? One approach is have more policemen and have them go out and catch the thief itself. You see, the strategy is then you put 100,000 policemen to catch this. What you just did is to reduce L because it will be bracketed. No matter where the thief is, it will be bracketed by a distance. So you dramatically reduced L. That's how you reduce the time. There's another way, which is how there's 2 ways of fishing. You can sit somewhere, drop a line, and wait for the fish to show up. Or you can throw a net and pull the fish in. Of course, if you throw a net and push the fish in, that will be much faster, and you can beat the diffusion limit. So I'm going to show you experiments on that. And this is the one that is commercial, that you generate locally. If you generate locally, then again you are making L small, and therefore your detection will be faster. So these three approaches, all playing with L and D. And in fact, the D, the way it comes in, here you use a proxy. You don't detect the original molecule, but you detect a messenger, which is much lighter and can diffuse much faster. So therefore, the reason this approach is not only it changes L, makes it small, but also it enhances D by an order of magnitude. These two allows you to detect things simply, faster. So this is how this police strategy works. Throw in more policemen and hope to catch the. So this is called a floating Eliza. So those of you know who Eliza, would be a floating version of it. Let's say that's the molecule, red molecule you want to capture, and this is your ultimate sensor, and I'm coming to that. And so the way you do is first you throw in one set of molecules, and this will be like your policeman. And as it is diffusing around, molecule is diffusing around, eventually it will be captured by those. And you can assume that these are large enough so that they are not moving at a high speed compared to the molecules. So quasi-stationary. If you want to do a full simulation where everybody is moving, no problem. Of course you can do that. But fundamentally you can see the result will remain the same. And then what you do, you bring in the other molecules, which only recognizes that, and then it's sandwiched. And then you wash away, and with a magnetic field, pull the molecules in here. So you catch and then transport the captured rubber to the sensor. So this is how you can get attomolar, because your now L is extremely small. You can have millions of them in the solution. And it turns out that the math is very simple, because I come from a semiconductor physics background. In a semiconductor physics, if you have defects, if you inject a minority carrier in the base of a transistor, and you have 1 million defects there, very soon one of those defects will catch the molecule, and this will lead to recombination. So I just copied up from Shockley's book the diffusion equation with a recombination, but this time the recombination is proportional to the number of magnetic particles and proportional to the number of molecules that we are willing to, where we wish to capture the rho. It turns out it's analytically solvable. You can solve how long will it take before the molecule disappears. And on average, you can show that the time to capture beyond a certain limit is independent of the number of molecules. It simply is defined by the number of magnetic particles. Do you understand why? Because if you throw more, the box, the virtual box, will become smaller and smaller. And so therefore, this box becoming smaller and smaller makes this one inversely proportional to the capture probe. This is a magnetic particle capture probe. Of course, the molecule still has to diffuse. Therefore, the D is still there, and the A naught is still there, but it has to sort of is direct inversely proportional to the magnetic particles. And so, so let me on that. So I don't want, I'll show you the effect of this in the final slide that summarizes all this. But this one you can easily show it's possible to detect attomolar level concentration. What about the second strategy? So let me tell you the second strategy. So the second strategy has to do with, you have to beat diffusion. But now you have to beat a diffusion by combining two things. One is that there is something called a lotus leaf, right? Lotus leaf, why we have something like a lotus leaf, super hydrophobic or hydrophobic surface, and the leaf wants to clean itself. So this is why, that's why these drops are very, very mobile. And so this is one thing, that if you have some analyte in here, it will be great because it's confined. But the problem is it runs around everywhere. On the other hand, if you have a coffee ring in the morning, that's the other extreme. Here is good thing is that the coffee ring doesn't run around everywhere. You have a coffee drop. It evaporates, but it evaporates on the corners of the coffee ring. In the middle, so you do not know a priori where the molecules are going to drop, especially if the molecules are very low concentration, attomolar or tens of attomolar concentration. The question we asked was, can you combine them? And if you can combine them, can you enhance detection limit? So that will be the second way to beat diffusion. So this is the idea. The idea is that, so we created a asymmetric structure where these are electrodes. So we'll do impedance spectroscopy. So these are one set of electrode and the other set of electrode, but the electrodes are designed in such a way so that the surface is super hydrophobic. But this is super hydrophobic in a very strange way. It is super hydrophobic in one direction, but it is sort of, there is no energy barrier in the other direction. It is just trapped by the edges of the electrode. Now it's like a coffin. The molecule has nowhere to go. It must then start from here. This is a cross section along this direction, this bulge. And then it will gradually evaporate. And as it evaporates, it will bring its cargo or the molecule concentration down at the sensor. It will precisely drop where we want it to drop, unlike a coffee ring which can spread things around. So it combines them both. And the reason it combines them, because we made the surface asymmetric. Okay? So how good is the result? It turns out that, first of all, you can, these are different concentration. This is your measuring impedance. So you put a little droplet and let it evaporate. And in the beginning, you have a certain concentration. And as the droplet is evaporating, your effective concentration is changing. So you have many data points. Yes, these things are getting more and more concentrated. So you have your impedance is changing. And for different initial analyte concentration, these are all DNA, analyte concentration, you will have a different impedance. And at each point, you can do a frequency sweep. So this is something you do, right? That starting from 10 in your case to a couple of thousands, but we always find in the order of 100 hertz or 220 hertz or so, you get the maximum sensitivity. But this gives you a remarkable enhancement in sensitivity for the following reason, because now you're probing the droplet as it is evaporating in 2 dimensions. You are evaporating in frequency and in time. So it is like, you know, if you wanted to compare, it is like a black and white endpoint detection. You take a single frame, single picture, versus a movie, because you can view this to be the color. It's a color movie. This is a color, and that's the frame as a function of time. Because you have this huge amount of information about that particular droplet, rather than just having the endpoint detection. Endpoint is just one. You have a measurement before and after. Because you can probe it all throughout the range, then as a result, you can get sensitivity which would be impossible in any classical system without the evaporation, without the data analysis this way. So this is the second way. One is throw in more policemen, capture it. Second is bring them down so that you can. So the third approach I'm going to is local generation. So one way people do this is that there will be on a droplet, there will be millions of beads in an emulsion, and each one of the beads, so this is how genome sequencing works. On each one of the bead, there is DNA is captured, and then through PCR, it is amplified. I'm not going through that. Last time when I came, I gave a talk on genome sequencing. And so if you don't, you can probably view it also on the Nanohub if you really want to. It's beautiful, beautiful work. Hopefully some of you will take a look. But the bottom line I want to put is that then what happens, this is a microchip. So there are nowadays about close to 1 billion transistors, and there are a couple of 100 million of these wells. Each well is about a few micron or so. Now, each one of the beads, so you randomly throw in the bead, and they get randomly loaded up on this wells, and then the reaction happens. So here we have the DNA, and you synthesize it back, make it double-stranded by bringing in ATCG, and every time there's a correct match, there will be a proton released, and you detect the proton. So this is what I was saying, that instead of detecting the DNA, which takes a lot of diffusion time, use hydrogen as its proxy, which diffuses much faster. And so once you have the correct detection, there will be a corresponding pulse as you are building this, and therefore you can read this genome. The main point in this context, I mean, there are, of course, a lot of technological things, but in this context, the way they bid the diffusion limit is because now the bead is within a micron of the sensor. And the sensor, the molecule that you're detecting is a proton. And therefore, it will diffuse very fast. As a result, you can detect within a millisecond. And the entire thing is about a second, where you have many, many samples that you can take. So that improves signal to noise, and that also allows you to detect at much lower concentration. So there have been, I often will point out that this is like 100 years worth of improvement in computer technology has been achieved in essentially last 20 years for genome sequencing using this approach. This is probably in mid-80s or early 90s. This is how genome sequencing used to look like. All right, so the summary of this part is that I showed you these lines before. And now what you can do by putting in more and more of this magnetic particle, you can essentially reduce the time, because it's directly proportional to the number of magnetic particles. You can reduce the time to capture even femtomolar concentration. You are no longer limited by the molecules diffusing to your sensor, because now sensors are going to the molecules rather than molecules coming to the sensor. And the droplet evaporation, it essentially takes a very low concentration and pushes the density high, because you are concentrating things. So therefore, that trick, you can do different tricks. Either you can push down in the vertical line, that is this approach, or you can push down in the lateral line, which is this approach. And so all these approaches essentially play a game with the diffusion limit by playing with the L and D. Now, let me go through a few of these about sensitivity. And the most important one I want to emphasize here is about screening. One thing we all know that we have to have salt every day, right? If you don't, when they are building pyramids, the favorite way of the pharaohs to punish people is to withhold salt. They didn't really want to beat or kill people, because then they'll have fewer labors to build the pyramids. They just used to withhold salt. And without salt, essentially the two DNAs are both negatively charged. They will simply fly apart. If you look at how much energy difference there is in the 4 billion electrons on one, 4 billion electrons on another, separated by less than a nanometer. Without salt screening them, there is no hope that they will stay together. So therefore, always all capture sensors essentially must have salt in this blue region when they want to capture a receptor with a target molecule or two DNA molecule coming together. Salt is fundamental. Now the chemists know salt, they don't know transistors. Electrical engineers know transistors, but they don't know salt. And so therefore all papers are therefore glass half full and most of the time irrelevant. And the way therefore one has to do this problem is one has to solve the Poisson equation, drift diffusion equation, but the most important thing is the salt must be accounted for. How do you account for salt? I mean, you can do it by first principle method, by looking at the structure and hydration and all those things, or you can do it simply, which is assume that the sodium, if it's a negative charge, the sodium will come and accumulate close, and the chlorine atoms will be pushed back, and there will be a double layer forming, and that will screen the charge. Now, And the effect is, and you can see one is an exponentially decaying with plus beta alpha psi, and the other one is exponentially growing. So you have a plus exponent and minus, that gives you the sine hyperbolic. Now you can solve it. This is not a problem. You can put it in a computer and you can solve it. But the thing is that it's a dramatic effect, because you can see what will happen, that when a biomolecule gets captured, most of the charges of this biomolecule, instead of coming to the nanowire, they get neutralized by the salt itself. Salt is like a floating electrode. It just catches all the charges because it's close by. And therefore, only a very small fraction of the charge actually comes to the nanowire. Rest are all taken up by the salt. Salt, you cannot, it's like a good and bad, Dr. Jekyll and Hyde, right? That it is necessary, otherwise they will not bind, but it takes a big tax so that as a price, because then it takes a certain amount of charge away. So the essential point is you can again solve this problem analytically. You have to have some faith in this, but the important thing is it's a logarithmic in density, because as you have more and more biomolecules come up, you have more and more salt coming close and taking more and more fraction of the total charge, and this, the nanowire only gets to see smaller and smaller part. That's why it's a logarithmic dependence on rho naught. If you didn't have a salt, most of the papers, if you read the EE literature, they will say ST is directly equal to rho naught. Because, you know, certain number of DNA charge came in, it's like a gate charge. So therefore, that's how much current change there was. But in practice, because the salt, there will be this logarithmic dependence. And you can see all the experimental data. These are all logarithmic, always logarithmic. You can look at salt concentration. You can look at time dependence. You can look at pH dependence. All contains the signature of salt in various ways, because it's all salt in different manifestation. And the only way you can capture all these experiments in a single shot is to account for salt in a fundamental way. So screening limit is fundamental. That's my point. Diffusion limit was fundamental. Now we solved it in some way. Screening limit is fundamental. What are you going to do about it? So there are a couple of things people have been thinking about doing. One is this idea that salt molecules are big and heavy. So why not do this measurement at high frequency? So you bias it. So these are presumably all the molecules, the DNA molecules, the black ones. And the salt molecules are screening it. So if you go beyond a certain frequency where the salt molecules cannot move and arrange itself dynamically, then what will going to happen that it will briefly expose in the AC signal. The screening distance will go farther out, and you will see more of the charge getting reflected in the channel. And so therefore, by using this critical frequency, you can effectively increase the length. It's like a foggy day. How far you see into it depends on the frequency of the light that you're using it. So here is sort of the frequency that allows you to see farther into the DNA because the salt molecules cannot move. So this is one technique. The other technique that we are working with Professor Bashir is something like this. And Piyush is here. It's basically his work in terms of theoretical modeling. The idea is that if you have a sensor, can you transiently move the charges left and right by applying a certain voltage? And if you do that, temporarily you can reduce the salt concentration and see the molecule. And before they have chance to dissociate, you bring the molecules back. So therefore, this is sort of relies on the difference in the time scale for association, dissociation. Now, whether it will work or not, that remains to be seen in terms of sensor response. But for the time being, this desalting appears to work reasonably well.
Would that desalting change the local pH around that electrode area, so that might lead to additional?
Yeah, so these things are all things to be checked, because the electrostatic potential is changing. Of course, the pH might change as well, something to look into. But what you can see here, that by applying a very reasonable field, you can pull all the charges like a battery. Pull all the charges on one side, pull all the negative charges or positive charges on one side, negative charges on the other side, so that the region in between, especially if you are at low concentration, you can deplete it altogether. And therefore, now you can detect it. The thing is that it must be finite volume, because if it were an infinite volume, had it not been a droplet, had it been a big thing, then of course, even if it took a certain amount of charge, that wouldn't have changed the bulk charge at all. So the finite size effect is very important in this regard. And so the point is, of course, that you need to desalt about a 100 millimolar. That's the typical concentration in our blood and physiological conditions. And with small voltages, difficult to desalt that level if the the droplet is too big. And you can see the basic idea. What you have, this trade-off is the volume, which contains the salt, and the area of the electrode. And what you have to make is this ratio, you have to make it as small as possible. Or volume versus area, yeah, as small as possible, so that once you sort of trap the molecules in here, then it can dissolve. And it turns out that probably classical electrodes will probably not have enough area to dissolve 100 millimolar, but probably you need a fractal electrode of some sort so that it has much larger area. And if you can reach a volume to area ratio about a micron, then you can dissolve in a physiological condition. So that's something to think about. This is ways to beat the screening limit. And finally, the screening limit, the best way to beat the screening limit is forget about charge altogether. So this is a work that we had recently been doing, is to combine MEMS with a transistor. So it's a flexure FET. So the flexure changes the capacitance, and that changes the corresponding current through this. Here, you don't rely on the charge at all. And because you don't rely on the charge, and also you don't have a light beam bouncing, you just detect it with the transistor itself. And that then can give you a significantly enhanced sensitivity because there is no salt screening compared to others. All right, very quickly then. Do I have 5 minutes, or is it?
We'll gladly listen to you for another 10 minutes.
Thank you. So let me, if I don't say about selectivity, then I'll be doing a very big disservice to the community. Many of the papers that come in important journals, none of them over the last 10 years have made it to commercialization, because they look very good on sensitivity, on settling time, femtomolar detection, attomolar detection, very impressive numbers. But what they fail is on selectivity, that they cannot differentiate between two molecules. And if they cannot differentiate between two molecules, then you really do not, that's not a sensor. That's a nice gadget, but that's not a sensor. And this is the fundamental problem of this field. And again, I want to emphasize that selectivity is fundamental. And it has to do with a famous problem called the car parking problem. And I'll show you what I mean. When we think about sensors, we think about the sensors to be a matrix, which is ideal. That is to say, assume that you have a 4x4 sensor, and our analyte is a vector. And let's say you have an analyte which will be responded to by sensor 1, and an analyte which will be responded to by sensor 4. And let's say these two are absent. Ideally, if you had an ideally selective sensor, then your response should be 1, 0, 0, 1. This is what you see. And then you infer that this exists. Right? This is what would be ideal. But this is, of course, there's no ideal thing, because the DNA all the time, even with a mismatch, it will still bind. And if it binds, the sensor doesn't know that it was not fully matched, because the total number of charge is exactly the same as before. It comes from the phosphate group on the backbone. So therefore, that you had one of them hanging and didn't match completely, it doesn't know. So therefore, it will give you a false positive. And the other that's energetics. The other thing is that when you have your receptor probes, then, of course, there are all these big empty spaces where a molecule come in, and it's like having a hole in the carpet, right? In the grass, if you see many times we have weed in our front lawn. And that's because anytime the grass is not there, weed can come in and sit down there. And for a sensor, it doesn't know that it is not really conjugated to the surface. It simply thinks there is a certain amount of charge, so therefore there is a conjugation has happened, it will give you a positive signal. Although, and especially because the fluid has, the analyte is very small, maybe a million times more dilute compared to the other proteins in the solution. So therefore, these false positives can completely kill you. And so what we looked into was the physics of how molecules absorb, but in a very simple way. One thing I do not know how many of you know, that if you throw, if you have your younger brother or a child, you can try this at home. Make a small box and throw a bunch of coins. And one at a time. This is very important. Sequential absorption. And the remarkable thing is that there's no way you can exceed 54% of the surface. It is not possible, mathematically not possible. 54% of the surface you can cover. That means 46% of the surface will fundamentally always be empty, and therefore susceptible to parasitic absorption. And this is always surprising, because when we know from the crystal theory that generally you can have a triangular, you can have 90%. This type of square, you can have 78% surface coverage, very high. But if you allow them to come one at a time, then what happens, even if you wait till infinity, then you cannot have more than 47%. That's why you have to incubate overnight. Sensors, if you don't do it, if you stop after an hour or so, in fact, most of the time it's difficult to get beyond 30%. 70% of the surface is actually empty. And so as a result, and this is not something complicated to experimentally verify. You can, polyethylene glycol surfaces, you can look at those surface coverage, and using this theory, you essentially can, the biofiling, that's what they talk about, because it's undesired in this particular case. And you can essentially interpret the experiment by using this very simple theory called random sequential absorption. Again, a fundamental limit that has got nothing to do with the technology itself. So you can then wait at different times. In fact, if you calculate the void distribution, and the longer you wait, you will get closer to the 54%. So how are you going to beat this one if the 54% is only covered even after you're waiting for a long time? So the thing that one has to do is to use smaller molecules to essentially plug the holes in the carpet. That's the only way, because then many of those molecules can come in and cover the regions which were previously empty. Because this 54% depends on the 54% is always 54% independent of the radius. But if you have two components, one is a large molecule and one small molecule, with a smaller molecule you can fill in the gaps, and so therefore overall you can increase the surface coverage. So that is one way to beat the limit. All right, so this is one way, and many people therefore do surface coverage. They take a lot of time to do the surface coverage properly. And the final one I will tell you about, that there is another way. I told you previously about droplet evaporation and how sensing can be done in solution as the droplet is evaporating. It turns out that many times you can see whether this binding has occurred or not simply by looking at its impedance. And this impedance, if there's a conjugation, there's a subtle change in the impedance. Previously, people didn't really notice this because the data was not enough, right? It was always endpoint detection, as I said, black and white picture at the end. But if you have a color movie, which is frequency and time, you get much higher resolution. And then it allows you, and I'm going very quickly, I know, It allows you to, if you repeatedly allow it to conjugate and deconjugate by increasing the temperature, you can essentially differentiate between perfect binding and imperfect binding. So perfect match, fully matched, versus partially matched and fully mismatched, you can essentially differentiate it by probing it in time. And that will be another way to get the selectivity. Okay, so let me end this then here. So I told you about 3 types of fundamental limits. The first was the fundamental limit associated with diffusion limit, and it is the geometry of diffusion, not the diffusion of any particle, the electrons or holes. It is the geometry of how molecules approach the sensor. That is one fundamental limit. The second fundamental limit is salt screening. This is all for electronic sensors. Of course, if you are having optical sensors, you are in good luck. You don't have salt screening per se because you are not really looking at the electrical signal. And the third one is this imperfect coverage, fundamental imperfect coverage. And those would be the fundamental limits. And how do you break the fundamental limits? Well, you put more probes into the system, you make the volume smaller, or you generate locally. And how do you beat the salt screening? Well, you can do higher frequency, or you can use the electrodes to temporarily remove the salt and bring things back. And at the end of the day, I just want to bring that picture back, because you see this one essentially both shows how the diffusion limit is important and how to break the diffusion limit by using geometry. So this is I'm going to make it my group photo. That this is because it taught me much about sensors, more so than I learned from the sensor literature itself. So my message is, to beat classical limits, you need neoclassical technique. And these are a few of them. Okay, so just to then conclude, I have a course which of course goes through this much more detail. Many of these things you can just, if you run a few simulation, everything will become much more clearer. And it is always important to do the theory next to the experiment, because without the two connecting together, it is often an exciting signal may actually be just noise. And it's important to know the distinction between signal and noise. That's it. Thank you very much for your attention and time.
You begin the lunch?
So in a way, you're not really beating the limit.
No.
Because you're just bringing the sensors close by, right? You're
Right.
still relying on random walk.
Absolutely.
And the proximity.
Yes.
One question on the 52% or so coverage.
54%.
54%. There is no interaction between the analytes coming down, right?
Yes.
Had there been an interaction, then it might have been different.
Absolutely. So this is called a random sequential absorption. When a molecule comes down, then there's no subsequent surface diffusion.
Or interaction between them.
Interaction between them, that is excluded. And that is what makes a crystal so dense, because as you know, the nucleation and growth will, this is the interaction that makes the perfect surface coverage. But in a salt solution, the molecules will not see each other, essentially. They're electrically screened. And so unless they can move around, 54% would be the limit. So it's called a car parking problem, because this was originally solved. This is analytically solvable, because if you don't have a markers in the street for parking the car, then it is very inefficient, because somebody may be pushing a little bit forward and there is a space in between. You cannot park another car there. And it turns out in 1D, 78% is the limit. You cannot park more than 78%. If you do 2D is 54%. Yeah, go ahead, please.
So, in your diffusion simulation, have you ever considered, so these biomolecules are charged in a certain pH of the solution. So if you have a device underneath that has some electric field, it depends on your biasing condition, how you measure everything. But so these charged particles, a protein of about 10 nanometers, will be trapped because of that local electric field.
Right.
And I presume that may enhance the time to detection by, perhaps by some order of magnitude. And maybe that's
It is true. It is true. So what you said just now is certainly true. I wanted to, in the beginning, wanted to look at large-scale things. Many of that size of the symbol itself probably is size of an order of magnitude. You know, it's a big symbol, big scale. So we wanted to first capture. We are a theory group, but not on how to design a specific sensor, but defining the principles on which work. Now, one thing I would caution, however, a little bit is the same way that the flow, whether it gives an, in the beginning it sounds right that if you have an electric field and if you have a charged molecule that it will pull in. But as you just saw that it has a very high salt concentration. In this salt concentration, you cannot even see a nanometer, 100 millimolar. You cannot see a nanometer into the solution. So you may have a lot of voltage and you cannot exceed before you start Faradic reaction. So, which is something that is a micron away. It doesn't know the electrodes exist.
Sure. I think, yeah, the question should have been at a, say, 100 micromolar. Or
yes, if you do it. Yeah, yeah. But one thing you'd see that many papers, and then again, the older papers, when they were reporting, you know, sub-femtomolar detection, in the discussion section at the very end, they will say, because I think the reviewers are complaining that this section is too low, they said that it must be because of the electric field that is pulling the, but that's only in the discussion section in the very end. But I think, as you can see, that normal physiological condition, very difficult, right? Yes, please.
So this 54% you're saying on the surface coverage, why doesn't that also apply to the undesirable quantity? So you're saying, you know, you can only get 54% coverage, so when you try to do the detection, all the stuff that you don't want, why does that then get priority?
No, it doesn't get priority. You can randomly, so you have 54% receptors, and let's say you have not done any PEG passivation or you haven't used molecules which have a larger fit to passivate the surface. Now the molecules are coming in. And this is a mixture of target and parasitic molecules. They will randomly sit wherever they can. And there is no preference. So they will randomly sit. Right molecule can also sit in the holes, or wrong molecules. But wrong molecules are generally so much larger in normal solution, unless you have done some filtration. It is so much larger, then they will always overwhelm the signal. If you do P-filtration, amplification, PCR, then that's a different story.
Sure. Yeah. But you're first doing like the probe incubation.
Right.
And that's usually done at an extremely high concentration.
Right.
And you're saying even then it still gets 54%.
Yeah, that's math. Yeah. Unless it can walk around on the surface and then pack itself. That's math.
I'm just curious, have you considered the effects on selectivity from this droplet evaporation technique? Because as you're decreasing the concentration, you're increasing also the concentration of the
Absolutely. Yes. So the question is very good. So that is why, you know, when the first paper came out, reviewers said, okay, I'm letting you go. Looks very impressive attomolar, but selectivity have to. So this is why we had been doing this. So this allows the selectivity. Of course, if it is significantly different in proportion, then it's difficult. But here you can see that depending on, so what you have to do here, look at both frequency and time, because there's time evaporation, and at each data point there is a frequency axis. So then you do a principal component analysis and do it like electronic nose people do. Like our nose has very relatively few receptors, but it can detect about 60,000 different odors. It is because it's not digital. Detection is not digital. Classical biosensing is digital. Did it bind or did it not bind? Yes or no. But the approach we are using here is principal component analysis. It's more like analog detection. And with it, you can detect, you can differentiate more than you would traditionally be able to differentiate. You cannot give a yes-no answer, but you can say the probability that is perfectly matched versus imperfectly matched. And there's no surface here. It's all volume. So there's no surface exclusion limit here. It's very early, so therefore I cannot say that it will succeed, but this is an idea that sort of says that this is a direction worth looking into. Yes,
Last
please.
question.
So you pointed out like 3 different fundamental limits.
Yes.
In terms of the diffusion, sawdowns.
Yes, yes.
And we can see families of papers that address one or the other. What do you think is the most significant between them that will give us, the next enhancement technique?
No, first thing is selectivity. If you don't have selectivity, then it's a good paper, but it's not really, it's not an engineering tool. And that's why, many of those genome sequencing things, first and foremost is the selectivity. Now, but the selectivity paper doesn't go into high-profile journals because that's where it's supposed to be engineering. But what I'm trying to convince all of you that these are all fundamental. Selectivity is no more fundamental than, or no less fundamental than sensitivity. Right? But selectivity would be number one. Even then, if I can, these days you don't need attomolar. Cancer cells, even if you could detect a femtomolar, that will be more than sufficient. Attomolar is extreme limit, and I think a much lower concentration would be perfectly fine.
Well, let's give another round to Professor Eliza.
Thank you very much.